Okay, today we're going to learn how to graph the transformations of quadratic functions. It's pretty easy. I think you're going to like it, and probably you've seen some of it before. The first thing we want to do is graph our parent function. We do have this in our journal. We have our parent function in our journal. So, but we're going to graph it again just to make sure we got it. So what we're going to do is we're going to put it in our calculator. I want you to fill in this table. We're going to fill in all these tables until we get a pattern going, and then we're not going to have to do that anymore. So we're going to graph our x values of -2, -1, 0, 1, and 2. We're going to do one more than it says to do. So as a reminder on how to graph things in your calculator, you are going to go to your home screen and you are going to say New Document. And it's going to ask you, do you want to save an unsaved document? The answer is no, you don't. So then we're going to go to, it should ask you if you want to add a graph, or what kind of thing you want to add. If not, hit menu and it'll ask you that. We want to add a graph, and it should say f of x equals at the top, so you can punch it in. If not, hit the tab key and it will come in. And we're going to say x squared. And I'm going to hit enter and it will graph it for us. That's our parent function. I want to look at the table so I can fill in my table real quickly. So I'm going to hit Control T. And I'm going to go up to -2, -1, 0, 1, 2 so I can see those. And it looks like it's 4, 1, 0, 1, 4. So I am going to graph those and put them on the graph that's on your paper. So go ahead and do that right now. Okay, so you should have your parent function graphed. I did my table. And now we're going to talk about the domain and range. They're going to ask you about domain and range on almost all these graphs that you're going to do, so make sure you know how to do it, and if you don't, you need to ask. The domain, remember, goes along the x-axis, so the question is how far to the left does it go and how far to the right does it go? Well, these arrows means it goes up and to the left forever, up and to the right forever. So it goes forever to the left, which would be -infinity, and it goes forever to the right, which would be infinity. So my domain is from -infinity to infinity. Now my range is a little different. This is up and down. How far down does this go? Well, it doesn't go down forever, you can see. It only goes to 0. So I'm going to start at 0, and it does touch 0, so it goes from 0, including it, so I need a bracket, and it goes up forever, so that would be to infinity. So again, make sure you know how to do domain and range. If not, ask as we go so that you can make sure and get that part right. Okay, now what we're going to do is we're going to graph each of the following quadratic functions on the calculator and explain how it's different from the parent function. So the first one is f of x equals -x squared. I want us to do a table on this one, and we're going to have to do tables on these until we get to where we see a pattern, and there is a pattern that we're going to see. But for right now, we're going to have to do a table. So I want you to plug in -2, -1, 0, 1, and 2. Use your calculator, same method we used to find the parent function, to find these y values, and then we're going to graph them, and we're going to see how this graph is different from the parent function. Okay, so I hope you got what I got right here. I got these values off of my calculator for my table, and then I graphed them, and so this graph is still a parabola. It's still quadratic, only it's upside down. Here's my parent function, and here's the f of x equals -x squared. So the only thing different about this one is that it's upside down. So we're going to say that it opens down. That's the difference between f of x equals x squared and f of x equals -x squared. The -x squared opens down. The x squared opens up. Another way to say that a graph opens down is to say that it's reflected across the x-axis. Here's your x-axis, and if it was up here, we reflected it across the x-axis, and so now it's opening down. So we could also say reflected across the x-axis. I think a lot of times that's what it's referred to, so make sure that you understand what that means. Okay, so the next one that we're going to do is h of x equals x plus 2 squared. We are going to do a table for this one. And I want you to use some different values for your table this time. I want you to use -4, -3, -2, -1, and 0 for your x values. So put the function in your calculator, get your y values, and let's graph it. Okay, so I'm hoping you got my same table that I got, and I'm hoping you got my graph. And this graph looks exactly like the parent function, only what is the difference? Can you see the difference between this one and the parent function? I think you're right. I think it moved to the left 2 places. If we look at our vertex was at 0, 0. Now it's at negative 2, 0. So it just moved left 2 places. So we're going to say left 2 units. And that is the difference between this function and our parent function. Now let's go to the next one. This time we're going to do g of x equals x minus 2 squared. And so we're going to make a table. This time, for your x's, I want you to use 0, 1, 2, 3, and 4. Find your x values, graph them, or find your y values, excuse me, graph them, and let's see what this graph looks like. Okay, so I've got my graph, I've got my table that I copied from my calculator, I've got my graph, and this one looks exactly like the parent function, only this time we moved. If our vertex was at 0, 0, it's now at 2, 0, so we moved to the right 2 places. So we're going to say we moved right 2 units, and that's how this one's different. Other than that, everything's exactly the same. Let's go to the next page. Okay, for g of x equals x squared plus 2, we're going to do the same thing, but we're going to use negative 2, negative 1, 0, 1, and 2 again. Okay, this next one, x squared plus 2, f of x, g of x equals x squared plus 2. I made my table. I graphed it, and it looks exactly like the parent function, only this time we moved up 2 places. So that's exactly what happens with this. We are going to go up 2 units, and that's the difference between this one and the parent function. Let's go to the next one. h of x equals x squared minus 2. We're going to do the same table. We're going to do negative 2, negative 1, 0, 1, and 2. Fill in your table and make the graph. Okay, here's my parent function, or I'm sorry, my new function. Looks exactly like the parent function, only this time the vertex moved down 2 units, and so that's the difference on this one. It moves down 2 units. Okay, the next one we're going to do is we are going to do number 7, which says f of x equals 2x squared. Okay, on this one we are going to do a table again. We're going to use negative 2, negative 1, 0, 1, and 2. Fill in your table and make your graph. Okay, this one looks a little different. It looks kind of skinnier than the parent function. It's still at 0, 0, but it's skinnier. And I'm going to show you how you can tell it's skinnier. If we go back to our parent function, and this would be a good thing to memorize, to get from my vertex to this point, I go up 1 over 1. And I go on to get from this vertex to this point, I go up 1, left 1. Then from this point, I go up 3 over 1. And same thing here, up 3, but to the left 1. That's a pattern that constantly shows up in these parent function graphs. Let's look at this one. This one has the same pattern. It goes down 1 over 1, down 1 the other way 1, and then from there, and then from, sorry about that, then from there down 3 over 1, and this one down 3 over 1. It's the same pattern. So down 1 over 1, down 3 over 1. This one went up 1 over 1, sorry, up 1 over 1, up 3 over 1. Up 1 over 1, up 3 over 1. Same pattern. This one, up 1 over 1, up 3 over 1. Up 1 over 1, up 3 over 1. Same pattern. And we go to the back. This function, it went up 1 over 1, up 3 over 1. Up 1 over 1, up 3 over 1. Same pattern. Number 6. This one goes up 1 over 1, up 3 over 1. Up 1 over 1, up 3 over 1. Same pattern. But this one, it's skinnier, so it's not going to have the same pattern, but look what it does. It goes up 2 over 1 and up 1, 2, 3, 4, 5, 6 over 1. Do you notice those? That's double what we did every other time. Up 2 over 1, up 6 over 1, and notice there's a 2 in front. So we're going to double everything on our pattern. This is called a vertical stretch, because if we took this and stretched it, it would make it longer and skinnier, and that's exactly what's happening. So we're going to call this a vertical stretch by a factor of 2, because there's a 2 in front of the x squared. And so that is your difference there. It's called a vertical stretch because we're getting skinnier. When you take Play-Doh and you stretch it out, it gets longer and skinnier, so it's called a stretch. Let's look at the next one and see what happens. This is g of x equals 1/2 x squared. I want you to do the same table. We're going to do -2, -1, 0, 1, and 2. Fill in your table and make your graph. Okay, so here's my graph on this one. This one is fatter or wider than my parent function, and that is because I have a 1/2 in front. So what this one does, instead of going up 1 over 1, it goes up 1/2 over 1, and then instead of going up 3 over 1, it goes up half of 3, which is 1 1/2, so I went up a half and one more and then over 1. So it does half of what the other one does. And so this one, this is like taking Play-Doh and squishing it down. It widens out and gets fatter. And so we're going to call this a vertical compression because we're compressing it. If you punch down on Play-Doh, that's compressing it. So it's going to be a vertical compression by a factor of 2. I'm sorry, by a factor of 1/2, because we're taking everything and cutting it in 1/2. Sorry about that. So it's called a vertical compression by a factor of 1/2.